welcome. Thank you for joining us today. I've been working in the architectural engineering industry for a few years, double digits, maybe 20 some odd years. And we've recently got into 3D printing, recently by, let's say, 10 years. Speaking of, the age of the industry, that's quite recent. The 3D printing industry has been around for a while. It's exciting to be part of this industry and to be a 3D systems partner. So speaking of 3D systems and the age of the industry, 3D Systems was founded in 1986, Rock Hill, South Carolina, and has created 3D printing offerings for a long time. 3D Systems invented 3D printing thanks to Chuck Hull, the inventor of stereolithography. So the expertise that we have at our fingertips is vast. So if Dolly or I can't answer your question, we will get you that answer. There's no question that we feel that we won't be able to address. We have a lot of assistance behind us. So at any time, please let us know. So talking about the industry, let's talk about the types of printers, or what is 3D printing. So basically 3D printing is additive manufacturing. There are a lot of different methods or technologies for manufacturing. Most common prior to 3D printing was CNC, or a subtractive process. So 3D printing is an additive process, layer by layer by layer. Let's talk about the different types of technology. So we have CJP, or color jet printing, meaning a binding agent is applied to a substrate. The substrate being a gypsum-based powder in the case of our Project 660 line. And we'll show that to the attendees in the office after the presentation. Basically, it's a printer that drops powder, and when that powder is on the build bed, the printer sprays a binding agent, kind of like a super glue kind of an agent onto the powder, solidifying only the part that gets hit by that material. Then you have SLA. SLA, short for stereolithography, is the most common 3D printing technology out there. And what's going on with my little presentation here? I'm totally jumping around. Then you have SLS, which typically stands for selective laser sintering. There's also selective laser melting, meaning that a laser is applied to the substrate, solidifying the material. Then you have multi-jet printing, and we have a multi-jet printer in the office, the ProJet 2500. There are quite a few technologies that 3D Systems offers that is considered under the MJP category, and we'll talk about that moving forward. But basically, the multi-jet printing technology is, again, applying a material through a jetted technology, applying both support and the solid material, or the finished product material, onto a build plate. And like I said, we have a printer printing in the office, and if you're unable to, or were unable to attend the live in-person event, please give us a call and schedule a visit. We'd love to show you around. Then you have digital light processing, or DLP. It's a process that essentially uses an ultraviolet laser and applies that laser to a liquid vat of material, again solidifying both the support and the actual finished part. It's a really interesting technology. Then, believe it or not, very popular lately, direct metal printing, or DMP. Again, a technology where you have granular material with a hardening application, usually again with lasers. FDM is probably the most common. People have heard of 3D printers, or who have only been exposed to a few 3D printers have heard about FDM in the form of the MakerBot or the plastic spool of printing, and that's considered FDM. Basically, when you're ready to print one of your designs, or as we like to call it, bring your designs to life, the typical format is STL. Again, STL is technically short for stereolithography, but the the technology, whoa, where did it jump over there for? But the technology is also called stereolithography. So the Stl format, although it stands for stereolithography, has been the go-to file format for exporting your geometry out of the design author software. Meaning that whether you're using AutoCAD or Revit or Rhino or some other application, the Stl is probably the most common format to export out. Stl having a couple of different options like binary and I forget the other one actually. This happens, getting old, Dolly was kind and didn't indicate how old I am, but I do have a lot of years of experience in creating geometry. So being an Autodesk reseller, Microsol Resources has an interesting combination of skills and offerings for you. So not only can we help you bring your designs to life by offering 3D printing services, we also can help you generate that geometry using the most common Autodesk or Rhino McNeil software. So Stl is the most common output. So whether you're in and we'll talk about the actual types of geometry software that's available. So like for instance, when I step back a minute, this is basically my presentation today. Talking about the 3D printers, we learned about the technology, and again, we can revisit that if anybody has any questions. Now we're talking about the available file formats, Stl being the most common. Then we'll talk about what does it mean to have a file format, printable geometry. Then we'll talk about the typical types of software. We'll talk about different ways of creating geometry, whether it's modeling geometry from scratch or actually capturing existing real-life geometry in the real world. This presentation is recorded, by the way, in case anybody has any questions. And then we'll go through and we'll talk more about it. So back to the file formats. Like I said, Stl is the most common stereolithography created by Chuck Hull 3D Systems. Stl is white though, so if you're doing an interesting design in your design author software and you want to export a model for printing, yeah, most commonly people think about the material defining the color. But in CJP or color jet printing, we're talking about an opportunity of adding color to the model at the printing process. So in your design author software, you would want to then export a format that brings the color with it. Stl is not that format. FBX, it's kind of interesting that it's the second file format that I'm bringing up. FBX stands for Film Box. It's an Autodesk generated file format, but has found itself all across the industry. Well, multiple industries, all across the 3D printing geometry creation world. So that FBX or Film Box file format is finding itself in Revit, in AutoCAD, in 3D Studio Max, in Rhino. Again, we'll talk about the geometry creation software, but FBX is a great output, and it brings the color with it, baking everything in one file. So no maps or materials are needed to be sent along with the file. OBJ is an interesting file format. It's been around for a long time. It's very useful depending on the output software. The WRL or the VRML, the virtual reality markup language or modeling language, is very similar to HTML, but it's interesting that this single file format creates your geometry or exports your geometry and brings with it color, materials, and textures. The only caveat with that is that when we export VRML or the WRL, it requires us to export and include those maps as well. So we could talk about the process and what type of software is best for creating geometry, but really it's up to the user. So what software are you comfortable with, and what do you want the output to be? This is a great option. And at a Rhino by McNeil, which we also happen to be selling for a good 20 years at least, I think, it's capable of bringing that with it. Just have to make sure to check the file formats and look for the texture inclusion option. BLD is just another one of those file formats. I've only included a few. There's an enormous number of file formats that different software applications are saving and exporting. We can import and open up almost any file format. So having all of these tools at our fingertips is definitely a plus. So no worries, no matter what you're creating your geometry or your design in, we're going to be able to help you out. The other thing about exporting file formats is solid geometry. We need a solid geometry or watertight file in order to 3D print it. So any 3D printing technology, whether it's 3D systems or not, is going to require a 3D solid file. What does it mean to be 3D solid? It means that it has to hold water, virtually, of course. So a watertight mesh means that all of the surfaces are complete. There are no instances where vertices do not touch or edges do not touch. As you can see in this example, over here are some edges that do not touch another edge or do not close or complete themselves. So this is an example of a partially solid and a partially not solid surface. As you know, when we're creating geometry or DWGs or drawings, a line really doesn't have thickness. You know, when we're printing it, sure, we assign a line weight to it. But in this case, this piece of geometry, that is practically no thickness. So when this goes to print, not only will the software scream and yell and complain, but the end result would be a surface that wouldn't even be able to support itself. So this would fail. So when it comes to troubleshooting geometry, we are experts in that field. We can get the geometry from your design author software and help you figure out the ways to make this transition to reality or bring your designs to life. So when we're looking at this piece right here, this is a great example of an image or a snapshot that I will capture and communicate back and forth to you, illustrating issues. I'll highlight points and issues of concern when we're communicating about getting something printed. When we do consider solid geometry or watertight, these are Googleable terms. So I'm going to show you a couple of great articles that talk about it, but basically you'll be able to find it. The industry is fantastic for assisting people in understanding what can come of it. What kind of software can I use to create a solid watertight file? You name it, we're going to be able to help you do that. So I think most of the people in the office are using Windows-based applications to create architecture and such. Anybody using Macintosh? Not in the office, but I'm sure somewhere online. Do we have any questions? No, I don't see any questions at the moment. Because we're an Autodesk house and a McNeil house, at the top of our list is Autodesk Applications, and these are just a few of my favorite. So as Dolly mentioned, I'm a BIM specialist as well as a 3DP specialist. BIM standing for Building Information Modeling. Revit is the most fantastic tool for creating architecture and engineering models for the purpose of visualization, documentation, and obviously 3D printing. So when you create a model in Revit, you're going to have access to a STL out option or simply export to FBX. One of the great, those are the two of my favorite options for exporting. It's right here available. So I have a couple of models in the back created in Revit architecture. Those models were simply exported as STL and printed. If I wanted color, I would do FBX. Revit is a fantastic tool. On a side note, besides 3D printing, if anybody has any question about Revit, that's one of my favorite things to talk about. 3D Studio Max or Autodesk Max or 3ds Design, Max Design. These are all the same products. Autodesk has now matured the product and called it 3ds Max. It is no longer Max Design. But anyway, when we're in that application, we're creating solid geometry by default. Revit also creates solid geometry by default, so it is a little bit difficult to create geometry in Revit or in Max that is not. Now, maybe I should hold off and say it's easy to create both geometry that is printable and geometry is not printable. It depends on your workflow. I know a lot of people who like to model with splines, and in 3D Studio Max draw line work and then extrude that line work into solid work. It could be, maybe not printable at the get-go, but there are a lot of tools that are built into these applications to assist us in doing just that. So 3D Studio Max has, STL out options and presets and things that will assist you in creating geometry specifically for 3D printing. AutoCAD, yep, creates the ACES surface, the 3D solid objects, by default when we're in 3D, so any extrusion, any kind of 3D geometry made in AutoCAD most likely is going to be solid geometry. Of course, if you take a series of pieces of line and just add virtual quotes thickness, that's not solid. That's not even a 3D surface. So you have to be careful when dealing with AutoCAD. But for the most part, if you're doing extrusions, your geometry is going to be 3D printable. And of course, I skipped over Maya, but that's another fantastic tool. And really, almost any Autodesk product that's out there is going to have the capability of creating 3D solid geometry for printing. Now to my favorite. Rhinoceros or Rhino from McNeil is a fantastic tool for creating you know, all kinds of geometry, architectural, product design, organic sculptures, organic geometry, even geometry that can be done with, you know, do analysis, surface analysis, reflection analysis. It's a fantastic tool. Like I mentioned, we've been supporting and selling that product for many, many years. I also have great access to really smart technical support people from McNeil. So at any point, and this has happened a number of times, a design is not ready to be 3D printed, we can actually send it back to McNeil and ask them for suggestions. At one point, not even a big client, you know, when I say a big client, a client that has, you know, multiple dozens of seats of Rhino, or a client that has one seat of Rhino. According to McNeil, according to us, it doesn't matter. So we got on the phone with a sole proprietor of an architectural firm, went a screen share session with tech support at McNeil, and we were able to solve the problems and patch. And it was a quick little learning session. Believe it or not, Google SketchUp, actually it's not called Google anymore. Yeah, SketchUp can be printed. It's a printable format, but the most time that people are doing SketchUp, they're not really creating solid geometry. They're creating faces, pushing, pulling faces, cutting faces. So there's a good portion of geometry that I've seen from SketchUp that is not ready to be printed. But there are a bunch. Yeah, we have a question in the audience. What do you have to do to make your objects? Yeah, there are a bunch of plugins and a bunch of tools. We even have a PDF from 3D Systems, like a white paper on recommendations. There are a bunch of tools. Like SketchUp is known for having plugins from, you know, to address a bunch of needs. There are plugins to assist in creating STLs and exporting geometry out. I have an architectural client, and I'll show you their model, completely done in SketchUp with materials and textures. So it can be done, but like I said, the majority, sadly, because of workflow problems, the majority of SketchUp geometry that comes out is not print ready, because it's just a series of faces. But you can solidify and Boolean and shrink wrap, and there's endless numbers of tools to help. And yeah, even though Bentley is a competitor, well, wait, they're a competitor and a client at the same time. MicroStation is a great tool for creating 3D geometry that's ready to be printed. Moving on, when that geometry is sent to the printer or sent to the software for analysis, we're going to do some error checking. And that's part of my job. So if you were to email 3dprinting@microsolresources.com, I'm going to create a report that discusses what errors were found or what suggestions I might have or how the materials are going to show up. So I'm going to go through a series of processes of checking for errors. And as I mentioned, that authored software is really responsible for fixing and responding to those errors, but we have some techniques and some tools to fix it in the 3D print software. So what is error checking and what are we looking for? So right out of the box, we're really concerned with the first option or the first level of concern, the normals, the face normals. If you haven't heard of face normals, they're visible or they're applicable for every piece of 3D geometry that's out there. And as you see in this image, the little arrows indicate how someone who was manually creating a 3D surface would generate a 3D face. So in AutoCAD, I remember back in the day, the command was 3D face, and you pick a bunch of, you pick 4 points, and you go in this counterclockwise rotation. the result will be a surface that has its normal facing outwards, away from the center of the geometry. That's a renderable surface, and it assists in closing the object to make that solid, watertight geometry. So in this illustration, all of the individual surfaces were generated in the same rotation in 3D space. All of those vertices were shared, meaning they're, coincidental or coincident, resulting in a geometry that has all the normals facing out. So that's the first thing we look at. And a lot of my 3D printing software will just automatically fix that because it sees the center of the object and it pushes all those normals outwards. The second thing is open shells. We're going to talk about that a little bit more detail in the Rhino example, but when I'm talking about open shells, it just means that similar to that other image I showed momentarily, it literally means that the, here it is over here, that's an open shell. So this face is considered a shell, and if it's open, then it doesn't close and make a watertight surface, resulting in an error. Shells with errors, whether it's holes or line work that overlaps the individual face. We're going to talk more about that. Rhino has a series of tools to assist in fixing those geometry, that pieces of geometry, and I'm going to expand it out over here and talk about that. So what are the methods for, one, modeling correctly originally, and then what are the error fixing commands and tools? Let's talk about Rhino. Of course, I could spend a day or two talking about the processes of creating error-free, 3D printable, watertight solids, and I'm developing a class at the moment just for that purpose alone. So creating different types of geometry from different industries and breaking them on purpose to show you of ways that we can fix them. So stand by and keep an eye out on microsolresources.com/training, and I've been putting that up in the next few weeks. But when we start learning about using Rhino, there's a series of processes, and this is somewhat in order of importance. So when you first get started, we're talking about tolerance. So you start with a Rhino model. You say, this is about what I want to create. I know it's a product. I know it's a building. I know it's a boat. I know it's a car or a toothbrush, right? So when you first start, you can use a template from Rhino, or you could essentially say, I want to start with a particular set of tolerances, particular set of things. So when we're talking about tolerances, we're talking about, setting the setting that dictates the maximum permissible distances apart that two objects or elements are permitted to be and still considered to be close enough for your purposes. What does that mean? When we move our cursor around the environment, you could see my cursor moving around like this, in different 3D geometry software, there's always an object snap or a world snap setting. So setting a tolerance in Rhino means that my cursor is only going to move a particular set of precision or a particular set of fraction of unit, right, depending on your unit. So setting a tolerance within your design software is going to mean that it is most likely to be closed when I mean to be closed. What does that, you following me? I don't know if you've used AutoCAD. Anybody in here in the office use AutoCAD? So AutoCAD, snap versus object snap, two different settings. Being architecturally trained, I studied at Arizona State University, environmental architecture. We started using AutoCAD and AutoCAD 3D. When I was going to school, I was also working for a company that built prisons, ironically. Arizona's a big prison state at the time. You'd never want to go to prison in Arizona, by the way, if you know the sheriff down there. It makes you wear pink. Anyway, sorry for the sidetrack. You're using AutoCAD, I'm building prisons. It's a complete masonry building. My snaps, my world snap setting was set to 4 inches. So that means my cursor never went anything but 4 or 8-inch modules. It's a perfect tolerance or perfect snap setting to make sure that you're not building a wall where some mason is going to have to cut anything but half block or full block. So we're not going to want to cut slices off CMU to create a building. We're also not going to want our surfaces to not intersect or touch or close Tolerance is the place of moving. Snaps is, again, like I said, snaps or object snaps. Again, making sure that your cursor has a series of tolerances to be constrained. The result is going to be an object that is closed. Then we start to get into some discussions. Hey, don't think dirty when we're talking about naked edges. We're talking about objects that are not closed, and in fact that edge is open to the space and not coincidental or closed with another surface. Then you have polysurf issues. So an open polysurf is similar to naked edges, but essentially means there's a hole or something not closing the internal volume. The command is cell open polysurf, or SRF. And as you type in Rhino, you start to type the commands. It shows you a series of commands that start with that set of characters. So it's really easy to find these tools. Of course, you can always go into the toolbar settings to figure that out. But then there's a command that will show you what objects are bad. So the select polysurface is also going to do that. It's going to highlight different colors and illustrate, what kind of problems the software thinks is happening, again, based on your tolerance. So Cell Bad Objects is going to highlight and give you an opportunity of selecting the objects that are bad. You go one by one. There's an actual dialog box that shows you, what it looks like. So I'm going to actually see if this link opens up. Open link. I don't want to, oh good. Here it is. Here's the McNeil wiki about fixing bad objects. What is a bad object? How do I know I have one? Use the cell bad objects command. Suppose I want to take them out and replace them. So extract bad surface. So there's an enormous amount of tools for working in Rhino to make it an object that's ready to be printed. So it's going to bring you to those objects. It's going to highlight those objects. Matter of fact, if you don't do these commands, Rhino will complain if the object has those problems in the first place. It'll tell you that certain numbers of objects have been selected, only a certain number have been exported when you do the STL. So if I actually just search Rhino Wiki Solid, it's another great, oh, get that little thing out of there. Another great resource. Brings me to a different page on the Wiki McNeil. How do I make a solid model? Enormous amount of resources. One of the other reasons why I love McNeil, I love Rhino. They really are doing their best to help you out. A wiki is obviously something that is contributed to from the community and from the industry as well as from the employees. So it's an amazing resource for your viewing pleasure. Things like testing water tightness. It's a simple option. You just start to type unify mesh, or you start to type cell naked mesh. Look at the length of that command. They're really easy to find. They're not difficult, and there's a lot of really good resources available to help you find that. But when you do finally go to export that geometry out of Rhino, you have an opportunity of getting a preview, like a simplified rough preview, which shows you how many surfaces you have. It will even highlight those edges that are open. So a flat shade modification to the view will highlight what that model looks like in a rudimentary kind of diagnostic kind of a way. Then when we actually go to export, we have options of saving geometry only. We have options for export only open objects. Well, that kind of makes sense. If I'm exporting an STL out of Rhino, I don't want to export things that are, are closed. Actually, this should say export closed objects. What would I want to export open objects? Essentially saying, hey, do I want to export the geometry only, or do I want to export everything that was in the Rhino model? So when I say export geometry only, it's not going to export line work, which is useful. They're of no use to me in the 3D printing world anyway, so it's amazing kind of resources. So I mentioned there was binary STL, which is my favorite, and then the ASIS. Again, this ASIS refers to solid geometry that the industry is very familiar with. It's the most common type of geometry out there, and it's an option for the STL. I usually stay with the ASIS STL. I'm sorry, I usually stay with the binary. But hey, you send us both, I'll tell you which one is better. Save small gives you an opportunity of lowering the number of faceted surfaces within a certain tolerance. It is a cool optimization if your geometry is I don't know, let's say simple. If the geometry is complex, that's not something you want to do. You don't want to lose resolution or lose smoothness. And then, believe it or not, plugins. This is one of many plugins to assist in generating STLs. So again, Rhino is a fantastic tool for doing that. Here's a series of other commands that are useful for fixing your geometry. Rebuild edges, unify mesh normals, match mesh edge. Within a certain tolerance, it'll close up your model and make sure that it's watertight. Fill mesh holes. That's a nice command. It's pretty straightforward. Anyway, so that's Rhino. If you have any questions about Rhino or want to purchase a seat of Rhino, Rhino 64 version 5 is out, and I heard discussions about a newer Mac version. Oh wait, maybe I wasn't supposed to say that. In general, when you're creating geometry, it is my recommendation to move everything close to the origin, scale it to the final size, because if I'm building a building and I want to export that to a print bed that is 10 inches wide, I'm going to have to scale the building down. Then I should check it for errors. Makes sense, right? So when we're bringing ourselves to 3D printing, we want to scale ourselves to the final printed size and then look at the geometry to see if I've modified or manipulated or created something that's not printable. This is correct. Yeah. Or, you know, whatever decibel. So the question in the audience was, when we're scaling it down, yeah, you're using your 1/4 inch equals a foot scale factor. You know, the gazintas, or, you know, like 2 gazinta 6 3 times. The gazintas are pretty interesting, and most applications have the opportunity of scaling it. I could technically scale it at the point of, you know, preparing your 3D printed quote, but what we're worried about really with the scale is the factor that when I bring things down to that printable size, are there going to be things that are not printable? Are things going to be too small to survive the printing process? Because yes, believe it or not, when I bring geometry down and scale it, maybe a house railing or a piece of glass is going to be, you know, a 64th inch thick. Well, that might be problematic. So depending on the technology, I will let you know what is printable, what is not printable. But, you know, if you're going to be using this and presenting this to a client, you want to be able to handle it. You want to be able to, you know, make something that's not fragile. So consider the scaling it down. Consider thickening things up. Anyway, set the units and convey that units to the printing team, meaning that if I'm using millimeters or meters or inches or feet, just let me know what the end output result is going to be. I will confirm it, believe it or not. Well, believe it or not, I will definitely confirm, hey, this is what we're quoting for you. This is the size that's going to print. Here's an example of the color. You know, matter of fact, some of our clients, well, a lot of our clients like to print in color. And when they do print in color, I give them options of printing a sample ahead of time, meaning a color swatch. I will print it out and give them test examples. A lot of times I will consider that as part of the overall cost. Sometimes, depending on the size or the quantity, I'll throw that in. So we definitely work with you to make sure that the end result is exactly what you expect. These are general options. I also think when I say move to the origin, every application has an origin. It also should be in the positive quadrant of that origin, in my opinion. 3D Studio Max, another one of my favorite tools. I've been teaching that to architects and engineers, as well as you know, people just doing visualization in general. It's a fantastic tool. Nowadays, it's only Max, so really, you know, there is no Max design nowadays. But if people have older versions, it's another great tool of creating geometry that's 3D printable. So in 3D Studio Max, if you're not familiar with it, as I modify geometry, that geometry history stays intact. So meaning I've done a push, I've done a pull, I've done a scale, I've done a twist, I've done a, a number of actions upon the original geometry, I can go back in any one of the, and it almost looks like a stack, like a list, or like a, like Photoshop has a history. Max has a history as well, so if I wanted to go back and change the extrusion, even though I've done 5 other actions after that extrusion, it's an option. But it's a good idea if you're ready to print it, collapse that stack, make sure that all of those actions have been applied to the final geometry, maybe even turn it into an editable mesh. Nowadays we have editable poly, we have NURBS, we have T-splines. So we want to simplify it and convert it to an editable mesh. Most 3D printing applications prefer mesh geometry. Then in Max, there's an Stl Check Modifier. So it runs through and highlights edges or highlights surfaces that are not closed or not solid or not watertight. In 3D Studio Max, there's a cool modifier called the Stl Check Modifier. You apply it to your geometry prior to export, and it runs through and gives you a bunch of options. When I export STL, you could do export selected, and the resulting STL will only be of the selected geometry. So if you have a large complex scene, or if you want to send me individual pieces, do a selection. Do your selection. You don't even have to isolate it. The export STL selected will do that for you automatically. That was 3D Studio Max. 3D Systems, or what we were previously a Z Corp reseller, has a bunch of options or suggestions for doing that. There are error checking pieces within the software. So what are you talking about? What 3D Systems software? When a client buys a printer from us, and we have about, I don't know, 30, 40 printers in the area, those clients will get a piece of software from 3D Systems that will allow you to do error checking and prepare it for 3D printing. So it does error checking, shows you all of the elements that are questionable. It does the face normals, it checks for open shells, it checks for shells with edges, and in general, here's a guide for best practices. It originally started with the Z Corp company. Z Corp got acquired by 3D Systems. So Z Corp basically started with the CJP, or the powder-based printing, where binder is applied to powder. 3D Systems acquired it and has improved upon it for the last 10 years or so. Anyway, this image is part of my 3D printing best practices PDF, or white paper, that's available online. If you would like that, shoot me an email, 3dprinting@microsolresources.com, and I'll share this with you. But it's another example of, hey, what is printable with this technology? This is definitely specific to a particular technology, but there are a lot of elements that are obviously universal. So here's maybe it's an extruded shape. There's a gap. Bang, that becomes nothing but a shell, an open shell. This would be better. It's a same type of geometry with a thickness that is closed. The result is a hollow space with a solid perimeter or solid geometry, right? It's not an opening in the surface, but an opening in a solid with a, it's hollow inside. Another example, right, hollow. That export, or that hole, is going to allow us to recover support material. In this particular technology, the Z Corp or the CJP technology, again, if you were in the office, you're going to be able to see the Projet 660 working, and that technology is the powder-based binder technology. So this technology is definitely unique in the industry. So the support material is the dry powder. So the bed is filled with powder, the binder sprays an adhesive or binder onto the powder, that solidifies. All the dry powder is essentially support, and when the print is done, I get to collect or vacuum up all of that dry powder. None of it goes to waste. The only thing that is solidified is your model. But by doing so, that would require us to do a little bit of adjustments. If I were to print something like this, like a cylinder, let's say, that's closed on the top, the powder would be captured inside that geometry. I would have to charge you for that powder as well. So when I say charge, we charge for the amount of material used. So in this example, if this was a cylinder with a cap, that hole would allow the powder to be collected, and thus it wouldn't cost you that. We wouldn't charge you for that material. You could print it like this if you want. That would be a solid brick. or a solid object, much heavier than this object. So anyway, so these images are basically repeating the same thing. Do I model a house with a gap? No, that's going to leave the powder captured in there. Do I model a house with an escape route? Yeah. Why not just get rid of this whole piece here so that the base of this house is completely open to below? That saves a lot of material. We only charge you for the material used. This really goes for all of the printing technologies. But as we'll learn, the different technologies use a different support material. Some support material has to be broken away. Some support material can be melted away. Some material has to be jetted away with a high-pressure water jet. Anyway, each technology has some best practices. We have that, we have collected those best practices, and we'll share them with you when you're ready. So 3D systems, again, I have access to those tools. If you have a printer, you will have access to those tools as well. AutoCAD. If you're an AutoCAD user, let's zoom in on that stuff. There are going to be some options for making sure that your geometry created in AutoCAD is the best that it can be, ready for 3D printing. Anybody know how to pronounce that? Nah, it doesn't matter. It essentially says to display the silhouettes or change the way that the geometry is rendered. The export result will rely on that to create a smooth geometry. Set ISO lines to 0. That again helps to create a geometry that is less faceted and more like the desired result. These things are pretty useful when you're dealing with curve or cylindrical objects. Same with facet res. It's a system variable to adjust the facet density based on the setting. If you type in facet res and it's asking you what the value should be, you type F1. Bang, it gives you all the explanations of the suggested results. Higher values creating a finer mesh, right? Only the solid and watertight geometries are going to export anyway, so we want to make sure that that geometry is exactly the way we want. This is kind of surprising. I didn't know that geometry created elsewhere in the the world space in AutoCAD would be less less ideal. Putting your geometry in the lower left-hand, putting your geometry so that the XYZ or 000 origin is the lower left-hand corner is very common for AutoCAD users. It is important to be in a positive axis or the positive quadrant when exporting surfaces to 3D printing. Again, it comes back to that idea of what is a 3D surface and how is a 3D surface created in a three-dimensional counterclockwise fashion. It kind of makes sense that if our geometry is in a positive quadrant, that information is cleaner and more ready to go. Simple STL out command, STL out, will generate that STL and start the process. Usually it says select the objects, then it goes ahead and tells you, do I want binary or do I want ACES? This is a little out of date, but Project Miller was a Autodesk test or Autodesk beta program. There's a lot of tools that have been developed by Autodesk to assist us in creating STLs. I'm going to talk more about that in a minute. All right. That Project Miller thing kind of graduated to a reality capture tool that Autodesk is now selling. It used to be called Memento. Now it's called Remake. That's one of the tools. And we'll share this slide deck with you, this presentation with you. And if you have any questions, I could point you to the video. But basically, if you were to just Google Autodesk Remake, this is no longer. Maybe I'll just kind of like cut it out and say, formerly Remake or formerly Memento. Formerly Memento. Okay? Remake is the tool. It's a fantastic tool for capturing geometry. Now, what does reality capture really mean? That means that we have a real-world object in three-dimensional real space sitting on our desk or out in the world. We want to capture that geometry, manipulate it, enhance it, recreate it. So reality capture means capture the real world, put it into my computer so I can reproduce it. right? One day we're going to have the Star Trek tool that sits in my office and generates Earl Grey hot, but right now we have to go through a certain process of capturing the geometry, putting it into 3D software so that I can optimize it and print it out. Reality capture can be scanned, so laser scanning. That means that I can actually go through and use a laser scanner to capture the geometry with color, put it into the computer so that I can manipulate it, scale it, maybe make holes in it, maybe adjust it to print it out. In addition to scanning, we can do photogrammetry, right? So Remake is actually very popular in the photogrammetry kind of world, but Remake also does manipulates the geometry from laser scans as well. What is photogrammetry? Photogrammetry is essentially the technique of using a series of photographs to capture reality and to create an actual 3D solid geometry out of it. I have some fantastic examples of those pieces that were photographed in the real world and then turned into printable geometry. It's a fantastic, fascinating technology. Autodesk is one of the companies leading that effort. So let me show you an example. Photogrammetry. What is photogrammetry? Right? The use of photographs or photography in surveying, mapping, measure distances between objects. It essentially means that when I go through and use software like Autodesk Remake, right? We're going and not just Remake. Hello. Autodesk Remake. How come Google doesn't know what I'm thinking? So Autodesk Remake, I have to sign in? Yeah, you know who I am. Autodesk Remake is essentially a tool. It wanted me to sign in because I already signed in. I have a different access to Remake. You can go out to Remake and actually try it for free. So Remake is that tool by Autodesk that's going to allow us to take a series of photographs or take laser scans, turn that geometry into real-world objects. It's fascinating. So basically, I'll let this run for a moment. I'm sure there's audio, but not necessary right now. So MRI scans, CAT scans, laser scans where it's handheld lasers, photogrammetry, taking geometry from the real world, bringing it into the computer to manipulate and recreate or reprint or just simply study. Fascinating examples. Photos, scans. I'm going to show you some stuff. Fascinating examples. We're running out of time, aren't we? Getting close to that hour. All right, so anyway, check out, just Google Remake, and you'll find some fantastic opportunities for that.